So today we're going to look again at the mean variance frontier in a little more detail. A big picture, where are we? We have three different representations: prices discounted payoff, beta representations, and the mean variance frontier, and they're all equivalent. Now we're going to look at it a little deeper. We're going to look at it with incomplete markets rather than complete markets, which we looked at the first day. We're going to use our state space geometry. That'll let us do infinite numbers of assets, and frankly, the new version's just a lot prettier. Let me start by reminding you how the traditional approach to the mean variance frontier goes. We start with a limited number, n original assets. I've plotted them here as the RIs. Then we start thinking about mean and variance of combinations. If we take a portfolio of two of them, that gives us this combinations of means and variances. We find the risky asset frontier, the best you can do with all of the individual risky assets. Then we think about what if you add a risk-free rate. That lets us draw lines between the risk-free rate and the risky assets. So we get finally the frontier, which runs from the risk-free rate to the tangency portfolio, and any portfolio on here is on the mean variance frontier. So we can get everything inside here. We can't get the stuff out of there. And any mean variance efficient portfolio is composed of two funds, the risk-free rate and the tangency portfolio. Historically very important because it tells you those two funds is all anybody needs if what they want is mean variance efficient portfolios. Algebraically, what's the standard way of going after it? We start with only n assets. So RE refers to a vector of n assets. Then we ask the question, let's look at the excess returns that are a combination of these n excess returns. To keep the algebra, I'm going to do just the excess return case on the board. The book has the case with actual returns. So what's our problem? Minimize variance of the portfolio, holding the mean of the portfolio constant. In other words, move this way as much as you can. That defines the mean variance frontier. So if the portfolio is given by a set of portfolio weights, we want to minimize. That's the variance, W prime sigma W, where that's the covariance matrix of returns. That's the mean of the portfolio. So that's our job. Do that minimization. How do you do that? Well, take derivatives with respect to W. That's what I've got up here, meaning each individual portfolio weight. Let's ask how much this changes when we adjust each of the individual portfolios. And that's our answer. Sigma W equals delta, a Lagrange multiplier on the constraint, times mu, the given mean return vector of the underlying assets. And there's our answer. So the optimal portfolio weights are a number, delta, the inverse of the covariance matrix of returns, sigma inverse, times the mean return. That's a big formula. You'll see that over and over again. At the heart of all portfolio optimizers that try to do mean variance portfolios is an implementation of that. It gets hard because inverting matrices leads them to blow up, but that's a numerical question. That's a formula you'll see over and over again. So we've got our answer. Algebraically, we found the mean variance frontier. The returns on the mean variance frontier are just mu prime sigma inverse, those are the weights, times the original returns. That forms a portfolio, and then you can scale it up or down. This is a one-fund theorem of the mean variance frontier because I'm only looking at excess returns. From that, we can work out what the mean and variance of things on the frontier are. The mean of that quantity is just mu prime sigma inverse mu. And delta, why is the delta there? Well, there's a whole bunch of different returns on the frontier. So as delta goes up or down, that scales the mean up or down. You can, if you want, solve that Lagrange multiplier and express things in terms of the given mean. The variance of something on the mean variance frontier, well, just take the variance of that quantity. That's mu prime sigma inverse sigma times sigma inverse mu. That's delta squared mu prime sigma inverse mu. And so we find the maximum Sharpe ratio of returns on the mean variance frontier. That too, as I outlined it in red because it's a formula you'll see over and over again, given means a covariance matrix, the maximum Sharpe ratio of all portfolios is mu prime sigma inverse mu, a very beautiful formula. Finally, the mean variance frontier, one of its many properties is the Rolle theorem. Returns on the mean variance frontier can be used as a benchmark for an expected return beta representation. The Rolle theorem comes out just from the algebra here. Let's look at our first order condition. Our first order condition up there. Sigma weights equals delta mu. What does that mean? Well, sigma times weights, that is the covariance. There's the sigma, covariance of returns, times the weights. So that's what that sigma weights term really looks like. Mu is the expected returns on the original assets. So what have we got? Returns times weights is a mean variance efficient return. So expected returns of all assets are proportional to the covariance of those assets with a mean variance efficient return. You're one step away from expected returns are linear in the betas of returns on a mean variance efficient portfolio, or the Rolle theorem, a single beta representation with REMV as reference returns that exists if and only if REMV is on the mean variance frontier and not the zero return, which is a special case. Graphically, I have the Rolle theorem here and the mean variance theorem here. What it says is that each of these returns should lie exactly on that line if we compute betas here with respect to any asset. This asset here, REMV, let's take with respect to that mean variance efficient asset. That asset has a beta of 1 on itself, of course, and therefore everybody else, this entire galaxy should lie on the line if plotted relative to beta. So we did the traditional approach to the mean variance frontier. Now I'd like to do the state space approach to the mean variance frontier, or Hansen and Richards' approach, because they're the ones who wrote the paper that showed how this works. So now we're going to lie in our state space. Payoff in state 1, payoff in state 2. We saw before how there's hyperplanes of constant prices, the excess returns here, the returns here, price 2 there, and a discount factor, or our friend X star, is in that space orthogonal to these hyperplanes. That's the space we're going to live in to think about the mean variance frontier. Now let's look at that a little more closely. I drew a three-dimensional version here. So there's the origin. Now we have a space here of excess returns. It's a three-dimensional hyperplane. And the space of returns is a plane in this three-dimensional space a little bit above. Let's locate the mean variance frontier in this state space notation. So we got to introduce a few new friends. Our first new friend is R star. So what is R star? We know that there's an X star. We spent a week thinking about there exists an X star in X and so on and so forth. So from X star, let us simply define a return proportional to the payoff X star. Divide X star by its price, and that gives us a return R star. Graphically, we take X star is a payoff, but it doesn't have price 1. So we create a payoff of price 1, R star, that's proportional to X star. A natural place to start because X star was the important payoff in our previous view of asset pricing. If you'd like an example of R star, well, the example of X star was price, expected payoff, payoff, prime payoff. So R star you can form by a set of returns in the same way. That's the X star, and then divide by the price of X star. So it shouldn't be mysterious. It's based on means and second moments, just like everything else we've been looking at. The second ingredient is a little more novel, RE star, the projection of 1 on the space of excess returns. This takes a little more to digest, but it's a beautiful quantity once you see it. So geometrically, what are we doing? Here is X star. Here is 1, a payoff that is 1 in all states of nature. And if you extend that, it becomes the risk-free rate, a payoff RF in all states of nature. RF is typically a little bigger than 1. So that's where 1 belongs, and that's where RF belongs. RE star is simply the projection of 1 onto the space of excess returns, as claimed. Now, why would anybody want to do that? Well, we're looking for a mean variance frontier. So we're looking for some way of changing means, and RE star carries the information about means in the same way that R star and X star carry information about prices. It's the same idea, just applied to means rather than prices. So for example, the price of X is E of X star X. In the same way, the mean of an excess return is E of RE star times RE. It generates means in the same way that X star generates prices. Now, how does it do that, you ask? What does that have to do with that property? Well, watch. The price of any X is the expected discounted payoff. And we can always project the discount factor on the payoff space and get the same pricing because the residual is uncorrelated with X. And the projector of a discount factor on the payoff space is X star. So that's how the price of X is E of X star X. X star is a payoff that generates prices. Well, let's generate means in the same way. An expected mean excess return is the expected value of 1 times the excess return. That's the same as the expected value of projection of 1 onto this payoff space, onto the expected return space times the expected return. And that, of course, is the definition of RE star. This may seem a little weird, a regression with 1 on the left and excess returns on the right, but that's exactly what we want. We want the set of excess returns, the excess return that is closest to 1. So we run a regression with 1 on the left and the excess returns on the right, and it generates means in the same way that X star generates prices. To further demystify it, how could we construct it? Well, the same way we constructed X star. Here's an example of an X star that works. The same construction, expected excess return prime second moment matrix inverse times excess return. That is an excess return. It's a portfolio of excess returns, and that has the required properties. It just takes 2 lines of algebra to check it. So here's our ingredients. We have R star and we have RE star. R star generates prices. RE star generates means in the same way. The hyperplanes orthogonal to RE star have the same mean in the same way that the hyperplanes orthogonal to X star have the same prices. So that's the point of RE star. It generates changes in means among the excess returns. Now we're ready to do our mean variance frontier with essentially no algebra whatsoever. 2 propositions which you can see in the picture. First, an orthogonal decomposition. Any return can be expressed as R star plus some amount of RE star plus a residual. So R star plus will go in the direction RE star, and then will go in another orthogonal direction to the residual. And these have some very special properties. First, they are all orthogonal to each other. R star and RE star are at right angles, meaning their second moment's 0, meaning the price of RE star is 0. It's an excess return. And the residual, eta, is orthogonal to both R star and RE star. That means that the mean of this residual is 0 because it's orthogonal to RE star, and the price of the residual is 0. It's an excess return with mean 0. So you can see that geometrically. How would you prove it algebraically? Just define eta as the residual and show that all these things are orthogonal and they have the required properties. Once you see the picture, it's just a few lines of algebra to grind out the required properties. Next, the mean variance frontier. Once we have the orthogonal decomposition, we can show that the mean variance frontier is just R star plus different amounts of this RE star, a two-fund theorem, just as we had a two-fund theorem before. Start by R star and then go different amounts of RE star. This here is in fact the mean variance frontier of returns. Why is that true? Well, take any decomposition here, take any return, find its mean. What's the mean? Mean of R star, mean of RE star. The mean of eta is 0. Eta is a 0 mean, 0 price object. What's the variance? Well, the variance is variance of this plus variance of that plus variance of this plus all the cross terms. No, the cross terms all went to 0. These are orthogonal to each other. That's what makes this so pretty. Well, if you want to minimize the variance, holding constant the mean, just get rid of that guy there, set the eta to 0. We've just proved our theorem. The mean variance frontier is R star plus WRE star. A very nice two-fund theorem based on 2 very different returns, suggestively similar to what we've seen before. You can see mean primes and second moment matrices and stuff like that. It gives you the same answer in an n-dimensional space, but a very different geometric representation and a different and I think and very interesting set of basis assets, the R star and the RE star, that'll be useful in many other circumstances to span the mean variance frontier. And we have a depiction of the mean variance frontier in our state space rather than just in the space of means and variances. So we have 2 very different pictures of the mean variance frontier. Let's try to relate them a little bit to get some more intuition for how these 2 pictures work. Let's compare the frontiers. So first of all, this object R star, which in our new state space picture was proportional to X star, where does that show up in the old-fashioned mean variance frontier? Well, one of its defining properties, it is the smallest. It's the minimum second moment return. How do I know that? Well, in state space, second moment is the length of a vector, and R star is since it's orthogonal here, it is the smallest length vector. You can prove that algebraically, or you can just look at the picture. R star is the minimum second moment return. Well, that property lets you plot it. Second moments, the mean of R squared is the mean of R squared plus the variance squared. So second moments are circles around the origin in mean standard deviation space. So R star is the minimum second moment. It's the return closest to the origin. There she is. R star, the most interesting return of all, is on the bottom section of the mean variance frontier. Next, let's think of this three-way decomposition. Any return is R star do E star plus a residual. How does that look? Well, we start with any return. We start with R star. R star plus W R E star, that sweeps out the mean variance frontier. So that brings us, for a typical return here, that brings us along the mean variance frontier. And then, as here we went R star plus W R E star, now we add the eta. Where does that show up here? Well, eta, the residual, that is a mean zero and price zero object. Mean zero means it doesn't add any mean to us. Price zero means it's an excess return. Furthermore, the eta, it's mean zero and it's uncorrelated with the other items, so it's a regression residual. It is exactly what we saw before. It's the idiosyncratic component, if you will. You can run a regression of returns on the mean variance frontier, and it's the unsystematic component. So we see again the theorem, only systematic returns are priced. The systematic component generates a mean. The eta is the unsystematic, if you will, component, the part that's not priced. More confusions. R star, it's down on the bottom section of the mean variance frontier. Is that wrong? No. R star is not anyone's portfolio return, and it's not the market portfolio return. You know, when we think of the CAPM or think of portfolios, often we'll have to add lots of assumptions, but we often think about portfolios being up there as being the good part. R star is not anyone's portfolio. It's a return that carries pricing information. A good word for it is R star is the return on the marginal utility mimicking portfolio. And that's different from the portfolio in your pocket. R star is X star over the price of X star. X star was the projection of the discount factor on X, and the discount factor is something like consumption growth to the minus gamma. So the discount factor goes down when returns on your portfolio go up. It's a measure of hunger. It's a measure of bad times. The discount factor is negatively correlated with the returns you might hold in your portfolio. R star is negatively correlated with returns on the top half of the frontier. So R star, it's a portfolio that carries pricing information. It's a portfolio that measures margin utility, but it's not a portfolio that anybody holds. Another comparison, our new portfolio in the mean variance, if we have excess returns only, the excess return, mean variance frontier, is of course just RE star itself. W times RE star, that's the mean variance frontier of excess returns, which is the one that I did algebraically. So how does that compare? The mean variance frontier of excess returns is just W times RE star. RE star was a mean, a second moment matrix times R. Lagrangian methods, we got mean variance efficient portfolios are a constant times a mean prime, a covariance matrix times excess returns. We're oh so close. And in fact, it's just two lines of algebra to show that these two approaches give exactly the same mean variance frontier as well as the same flavor, a mean, a covariance matrix inverse. So we are looking at the same object, and you can view things in mean and variance space or in state space. It's kind of fun to compare where each lies in the other space, but nothing tremendously different about it.
So where's the risk-free rate on this picture here?
Good point. So obviously we're doing lots of special cases here. In the state space case, I drew a case where the risk-free rate was a traded payoff. We could do it with the risk-free rate not a traded payoff, and I'd need more dimensions, and I'm kind of challenged to write 3 dimensions already. In this case, I drew the case where there isn't a traded riskless payoff. What would this look like with the risk-free rate? Then the mean variance frontier would look like this. That's what the mean variance frontier looks like with a risk-free rate, and it would look exactly like that. We would just go through the risk-free rate on our way up to the mean variance frontier. So in state space, we would start at R star, go through the risk-free rate, and get to the mean variance frontier. So that's what it looks like with a risk-free rate. That's what it looks like without a risk-free rate.
So is R star the tangency portfolio on the wrong side of the minimum variance frontier?
That's a good question. And okay, so this is not the risky asset frontier. This is a case in which we would have no risk-free rate. In this case, with the risk-free rate, the risky asset frontier would have to be up there somewhere. Yes, this has to be tangent because R star is the minimum second moment portfolio, so that the return can't cross that way. So I think we just proved it has to be tangent. Never thought of that, but it seems like it's true.
Clarify a little on the difference between the frontier in green and the frontier in red. You said that the red one was the frontier of risky assets. So what exactly is this green frontier?
So let's redraw this because this is turning into a mess, okay? You may want to. What I'm doing over there, come on over here, is there's two cases. Case one is when there is no risk-free rate. The risk-free rate isn't traded. And the case two is there is a risk-free rate traded. Okay, so when there is a risk-free rate traded, let's draw in the entire thing the way it's supposed to look. There is the mean variance frontier. There's our minimum second moment criterion. That mean variance frontier has a risk-free rate. It has an R star. And if we wanted to draw in a corresponding frontier of risky assets, that would look like that. That would be a mean variance frontier of all assets, not including the risk-free rate. It would have its own R star. There would be a minimum second moment there. This is a payoff space that's smaller. It doesn't have a risk-free rate, so it has a different R star, a different RE star. This is the case when we add a risk-free rate. Well, then that's what it looks like. Does that answer your question and make a prettier picture?
Yeah.
So just to clarify, the R star, the minimum variance second moment portfolio is not the same thing as the global minimum variance portfolio.
Right. Second moment is not the same thing as variance. So R star is the minimum second moment portfolio. The minimum variance portfolio in this case is, of course, RF itself. Its variance is 0. So there's the minimum second moment portfolio. There's the minimum variance portfolio. The minimum variance portfolio in this case, if we threw out the RF, would be right there. Now, more generally, there's an enormous amount of beautiful properties of all of these different items. R star, RE star, second moment portfolios, minimum variance portfolios, the case with a risk-free rate, the case without a risk-free rate, zero beta portfolios, spanning theorems, and so forth. We've just touched the beginning of this zoo, but these are some special cases to keep in mind.
In this context, I'm a little bit curious that how short selling constraint can affecting the link between state space approach and mean variance frontier approach.
Yes. So short selling and other transactions costs. One of the central assumptions I made going into this was there are no transactions costs. So arbitrary short selling is allowed. You can hold negative amounts of any security. No costs for doing so, no bid-ask spreads, and so forth. Now, what happens if we change that assumption? Everything gets more complicated. We don't just throw the theory out, and this is the general point that I want to emphasize. When we add realistic things like this, the basic ideas of these theories maintain, but you have to add all sorts of asterisks and corrections. So let's think what happens in the basic mean variance frontier. If you have a mean variance frontier and there's two assets, E and sigma, the portfolio of the two assets, that generates this frontier between them, that has positive weight on the two assets. In order to generate this part here, we have to go short this asset and long this asset, and that gets us up here. So that part of this mean variance frontier disappears when you have short selling constraints.
Right.
Now, let's think about that in state space. When I first introduced our state space, I said one of our assumptions is you can form arbitrary portfolios. What's going to happen when you have short selling constraints? Well, then let's suppose our state space is generated by that asset and that asset. Right? Well, then we can buy any payoff that's a linear combination of those.
Right.
If we add short sales constraints, then I can only buy portfolios that are here, because those have positive amounts of both assets in their weights. So now rather than an infinite plane, we're limited to a triangle, and we have to keep track of where the triangles end, and so on and so forth. It's going to make your head explode if you try to do that today. So now let's complete our discussion of the mean variance frontier with the Rolle theorem. The The role theorem we met a couple times, most recently as a consequence of the Lagrangian minimization approach to the traditional mean variance frontier, that all returns should line up with their betas computed relative to a mean variance efficient portfolio. Let's see the role theorem in state space as well. So that's our last topic. If a return is on the mean variance frontier and not equal to the risk-free rate, let's translate it to a discount factor. The theorem I'll show you is there then exists a discount factor linear in the mean variance efficient return that prices all of the available returns. In other words, I can find an A and a B such that there's a discount factor linear in the mean variance efficient portfolio, and then 1 equals E of MR. Of course, you know once you've found a linear M, that's the same thing as an expected return beta representation. That little bit of algebra we've done a couple of times, so you should be able to get back and forth there. So mean variance efficiency carries all that pricing information. Let's see that. Our goal is, let's see that theorem in the state space representation. So I've got here the graphical version of the same thing. We want to show if and only if. So here's our objective. How do we get our discount factor? In this case is just X star. I've got complete markets. I don't have enough dimensions on the board to do incomplete markets. So our objective is get from a mean variance efficient return back to X star. How do I find a X star? How to express X star as a linear function of a mean variance efficient return? Well, linear function means let's go to the mean variance efficient return. B times mean variance efficient return means stretching it. And then adding A means adding a certain amount of the one vector. So if I stretch out the mean variance efficient return and come back along the one vector, I get to my friend X star. We've just proved graphically that if a return's on the mean variance frontier, then by stretching it and adding a constant, I can get to a discount factor. I can price assets. I've got that information with a mean variance efficient return. And I can't do it if my initial return is not on the mean variance frontier. Let's try that one. Well, now I stretch out, I take an original return that includes some eta component. I stretch that guy out as much as I like. If I stretch that out or stretch it back and then subtract off the 1, I can't get rid of the fact that I'm too far to the side. I can't get back to X star. I'll always end up at X star and then something off to the side. So that's the if and only if. I can get back to X star by linear transformations if I start on the frontier, but I can't if I'm not on the frontier, meaning I can construct a discount factor from a mean variance efficient portfolio, meaning then I can express expected returns as a linear factor pricing model using that portfolio. Algebraically, here's the case with excess returns. Excess returns are always so simple you can do it in 3 lines of algebra. So I want to show that if a return is on the mean variance frontier and it's not 0, then I want to construct a discount factor and show that it works. So my representation means if it's on the mean variance frontier, it's just a certain amount of the RE star portfolio. Let's try a discount factor that is linear in RE star, and I'll try some eta there and see what happens. So what do I have to do? I just have to take E of M times RE. Let's try to price an excess return with that discount factor. What happens? There's my M. There's my arbitrary excess return. Now, take the expected value of that product. What do you get? Well, 1 times RE star is RE star. RE star times RE star is RE star squared, but RE star times any excess return generates the mean of that excess return. So those two things are equal and go away. Then I've got the eta term, E of eta prime, and all the cross terms are 0 because everything's orthogonal. So I'm looking for 0 here, and I've got 0 if and only if eta is 0, i.e. if my original return was on the mean variance frontier. So that's the same logic that we use in the more general cases, with and without risk-free rates, with actual returns. You just have to show algebraically, try an M of the right form, and show that that M works if and only if the return is on the mean variance frontier. So there's the role theorem in its payoff space representation and connected to discount factors, completing our tour of all the various different representations of asset pricing ideas. So we've done a lot of stuff, and it's time to summarize and take stock. We've looked twice at existence and equivalence and different representation theorems. And now let's talk about what they mean and why they're useful. Here's sort of a schematic of what we've done. We've looked at asset pricing in a couple of different ways. Prices expected discounted payoff, expected returns or linear and betas, or something's on the mean variance frontier. We've looked at continuous time representations or discrete time representations, and we translated discounted payoff into a set of risk-neutral probabilities. And you've learned how to go from each of these to the others. Given any of these representations, you know how to construct one of the other representations. You understand they're completely equivalent. We did some existence, too. The law of one price means there's some discount factor, or no arbitrage means there's a strictly positive discount factor. That's similar to, in order to construct a mean variance frontier, you need a non-singular covariance matrix so that you can invert it. That's the same thing, really, as the law of one price. So the existence theorems and the representation theorems just connect all these many different ways of looking at asset pricing and tells you what it takes for any of them to make any sense. What do you learn from all that? I think there's two big lessons. First, price equals expected discounted payoff, or any of these representations, by themselves don't tell you that much. They exist if there's just no arbitrage opportunities, which is a very weak condition. If you want to test asset pricing models, if you want asset pricing models that are going to work out a sample in particular, connecting the discount factor or the risk neutral probabilities and so forth to data, figuring out what the factors are, that is where all the meat of an asset pricing model is. Second, since we have so many different representations, use the representation that works best for the application you have. Finance is not a deep theory field. It's a practical application field. And each of these has its adherents because each of these tends to make life simple in certain applications, but know how to translate them. It can provide a lot of insight if you're doing risk-neutral probabilities to understand that really that's the same thing as the statement of something's on the mean variance frontier. So I advertised that the representation and existence theorems are useful for understanding why you're doing what you're doing. Historically, they've been very useful that way, and letting you know a little bit about where they came from historically, I think will make that case and let you see how you might use the theorems in the same way in the future. Fama in 1970 introduced the concept of market efficiency, and we studied that on the first day. For example, running regressions of returns on variables seen at time t to see if you can forecast returns. Those were tests of are markets efficient, do prices incorporate information. And his early and continuing antagonists held no, markets are irrational. Now, what does irrational mean? Irrational must mean that the probabilities are wrong. People don't assess probabilities right, so markets don't forecast things right. Fama already proved a theorem in 1970 called the joint hypothesis theorem. He said any test of efficiency is a joint hypothesis with a model of market equilibrium. Let me translate that into modern notation, into the concepts we've used a couple different ways. One is, let's look at excess returns. The true model is not that excess returns are unforecastable. 0 equals E of MR means that if I take the product of M and R and regress it on something, that should be unforecastable, not returns itself. To test forecastability, it's a joint test of a model of market equilibrium, something about the discount factors. They always enter together, and unless I can tell you something about the discount factors, I can't tell you anything at all. Another theorem we've looked at that gives the same sense of Fama's theorem. Price is expected discounted payoff, and notice that the probabilities and the marginal rates of substitution always enter together. So you can't tell me the market has the probabilities wrong unless you tell me something about where do those discount factors come from? How do we connect those to data or to theory or something? A third theorem we've seen that expresses Fama's joint hypothesis question is that for any set of probabilities, if there's no arbitrage, then there's a discount factor such that the price is expected discounted payoff. Whether those probabilities are right probabilities or wrong probabilities, all we need is the absence of arbitrage. We can find a discount factor to make the prices right. So the pricing representation, prices expected discounted payoff, expected discounted returns, that's easy. That holds quite generally. What matters is the model of market equilibrium. An implication of this is there's nothing you can do on asset market alone to prove rationality or irrationality or something. You need to introduce some information about what this discount factor is if you want to argue about rationality and efficiency and so on and so forth. Second historical context, the Rolle theorem I've mentioned quite a few times. Why is that theorem so important? Why did that guide what people thought about? Well, when Rolle wrote in the late 1970s, people did tests of the CAPM. Expected returns are linear in betas on the market portfolio. And, they were finding results that sort of say in the 70s, yeah, sure, it works. Now, where does that come from? Well, to get to the CAPM at the time, people used a lot of assumptions. They used assumptions like quadratic utility, and then there's this question of what the market portfolio, it's supposed to be the wealth portfolio, does that matter? People said, well, it's just a proxy, don't really worry about it. Or, expected returns equals beta times lambda, that has all the economics in it. Well, when Rolle proved that no, that representation just means that this portfolio returns on the mean variance frontier, all of a sudden we could see that the existence of a beta representation is trivial. What counts is the identity of this mean variance efficient portfolio. The idea that this is what mattered and that the market return is just an innocuous proxy for the wealth portfolio. No. This, in fact, is easy. The identity of the portfolio return, the fact that that return should really be on the mean variance frontier, that's the entire content of the theory. Rolle wrote, in fact, that he thought the CAPM was untestable because we need to measure the wealth portfolio, and all we can see is this market portfolio. Who knows if the market portfolio is really on the mean variance frontier? Well, you can see the theorems guiding how we think about what we're doing, guiding the sense of argument about are markets rational or irrational, is the CAPM right or is not right, and they continue to guide us in thinking about what we do for the application that we have in hand today. So more implications of these existence and representation theorems, ways to use them to make them come alive for you. All of our theorems, our examples, had quantities like expected returns, second moments, and so forth. And you might have wondered which probabilities. What if I use the wrong probabilities? Are those agent probabilities, or sample probabilities, or rational probabilities, or irrational probabilities? The answer is these theorems hold for any set of probabilities. Now, in particular, that means they hold for the sample probabilities, the frequency that something happened in sample, as well as the subjective probabilities in people's heads. That is an important implication. Let us form a sample discount factor by the sample price, sample second moment matrix, and the sample payoffs. Or, let's be even more clear as an example, let's form a sample, an in-sample, ex-post mean variance efficient portfolio. By the sample means sample covariance matrix, and use those to form a portfolio. Well, our theorem says a mean variance efficient portfolio generates a beta pricing model. If you do this, you will generate an absolutely perfect fit in sample. You can find a portfolio. This is a portfolio. That's a set of weights. There is a portfolio out there, the ex-post mean variance efficient portfolio, that makes an asset pricing model, use a linear pricing model, a one-factor pricing model, look absolutely perfect. Run that regression of returns on the mean variance efficient portfolio, put that beta in there, and lo and behold, you will get a perfect fit. We just proved that. It's a theorem. You can prove it by computer if you want as well. There is a portfolio which perfectly prices all assets in a given sample. Now, that has deep implications for how we conduct empirical work. Now, you might say, well, that's great. Let's find that. But of course, that one works terribly out of sample. The ex-post mean variance efficient portfolio, it contains all the luck of a sample. It's the I should have bought Google at the IPO portfolio. It contains all that ex-post luck. That advice is particularly useless for what should I buy today. It's not at all a good hint to what's going to be mean variance efficient or price things in the next sample. It's a regression with the same number of data points as right-hand variables. It fits by construction in a sample, but it's terrible out of sample. Now, that theorem means that when we do empirical asset pricing, let's go back to Fama and French, which I brought up as the case, one of the most classic empirical asset pricing papers ever. They used a set of portfolio returns. Well, what kept them from just discovering a mean variance efficient portfolio? We know something that's better out there than the Fama and French portfolio. What kept them from just rediscovering this? So that's not the first set of portfolios that anybody ever tried. How do we as a profession avoid just rediscovering the sample mean variance efficient portfolio? Well, by whatever rules of the game we impose in order to keep us from fishing around and finding this portfolio. If you fish around long enough, there's a perfect fish in that sample. So the rules of the game for empirical asset pricing are the entire content. And I wish I could tell you there was a lot of science in that rules of the game. There's a lot of art, but that art is in fact extremely important. In Fama and French, you will see that art. They don't have a big theory, but they have some beautiful prose about state variables for investment opportunities. And they stop at momentum, where they could have easily made something like that work, but they didn't feel like that passed the rules of their game. That's a fine art. It's a very important art. And this theorem tells us why it's such an important art. Because you can go fishing, and out there is the most perfect fish in the world. So another case where the theorems, I think, give us an important guidance to how we do asset pricing, how we evaluate asset pricing, how we think about what it all means. The mimicking portfolio theorem, which we've used a couple times, and let me make it explicit. Suppose you have a pricing model. In fact, suppose that the consumption pricing model worked perfectly. So price is expected discounted payoffs using consumption growth to the minus gamma. Well, then we can always represent the same prices with a mimicking portfolio. A mimicking portfolio is the projection of that discount factor onto the space of payoffs, a traded portfolio that carries all the pricing information. How do you do it? Well, you run a regression of M onto the space of payoffs with a residual. Residuals are uncorrelated with right-hand variables by construction. So that's the same thing as projection of M onto X times X, which is just our friend X star. So if this model worked, we could construct an X star just by running a regression of marginal utility onto the space of all returns, and that X star would generate prices exactly as well as the original consumption growth model. The mimicking portfolio theorem. Now, what does that mean? There's a portfolio that prices just as well as the true discount factor. And we also know from our last fishing theorem that there's a lot of portfolios that will price a whole lot better in a sample because they fish their way around to something closer to sample mean variance efficient. Furthermore, if consumption isn't measured that well, then the mimicking portfolio for consumption will price even better than true consumption and the true discount factor, simply because that can be much better. Asset returns are much better measured than the true underlying discount factor. So what do these easy to see theorems tell us about how we do asset pricing? First, it tells us a common exercise. If you have a utility function or consumption growth, a common exercise is to run a horse race. Does my discount factor beat the Fama French three-factor model or whatever portfolio-based model is current? But that's a silly thing to do because we know there's a portfolio-based model that does just as well, the mimicking portfolio, and we know you can fish around and find better portfolios, and we know the portfolios are better measured anyway. So doing that horse race is silly. Really, the status of a consumption-based model is its greater theoretical purity. What we should be doing, which makes more sense, is to ask whether Fama and French's factors are the discount factors for some model. Does our model explain why those things work? That's a much more reasonable thing to ask. But a horse race between ad hoc factor models and macro-based models just doesn't make any sense at all because of our mimicking portfolio theorem. On the other hand, what does the theorem tell us? Using the mimicking portfolio is right for most practical questions and would be right even if we had the true model, which we don't have. If you had the true model, you get consumption data quarterly at best. You want to price something in sort of real-world pricing on a day-by-day basis. You want to find out whether the latest anomaly is just a version of all the other anomalies we've seen. For that kind of purpose, you don't need to go back to the deep underlying discount factor. You use the mimicking portfolio because that has good data on a daily and weekly basis and can let you know, is something new just a version of the old ones we've seen? That's an example of a practical question for which using the mimicking portfolio would be better even if we had a perfect model. But of course, using mimicking portfolios, using ad hoc factor models, they can't do anything to answer the rationality question because for that you need to tie it back to real macroeconomic risks. So these are examples why these theorems and alternative representations are important. They guide you to thinking about what the heck you're doing and to using the right kind of model for the question you have at hand. We're not always arguing about rationality. We're not always just trying to price one thing given the price of other things. We're not always fishing for anomalies. Use the right model ask the right questions, and these theorems can be an important bedrock for you to do that. So one last question on our representation question remains: what about conditioning information? The model that we've looked at really is the price at time t is the conditional expectation of tomorrow's discounted payoff. Or in expected return beta language, the conditionally expected return depends on today's beta and today's factor risk premium, and those things can vary over time. This wouldn't matter if we lived in an IID world, if every day was like a coin flip and conditional expectations didn't vary over time. But we saw a hint in the first week of the fact, quite more generally true in empirical finance: conditional moments vary a lot. We saw in the first week, by running returns on dividend yields, that conditional mean returns vary over time a lot, and that's even truer for individual assets. Covariances and betas vary over time a lot. Variances vary over time. That's the lesson of the Garch conditional variance world. We live in a world where information varies over time a lot, so we can't just ignore this issue. It's a deeper issue too, and I want to sensitize you to the word information set, because so many people get this fuzzy at least. When you say ET, what information set generates that conditional information? Is it the information, when we say conditional information or conditional covariance or conditional beta, is the information set on which that's conditional what's in an individual agent's head? What's in some sense, the market's head, the intersection, or is it the union of individual agents and all the information they see? You know, they see, the agent may see, he knows his brother-in-law who gave him a stock tip. Well, we don't see that. Is it the information set generated by all variables that we see? So we can run regressions on a lot of variables. Or is it the information set, the conditional mean from the variables we might choose to include in a particular regression? This is the conditional expectation of return given the dividend yield, but not given the VIX and all the other things that we can see. Or are we talking just about an unconditional expectation? Well, lots of different information sets, and one lesson in life is always to be clear about which information set you're talking about. I brought this up to make you feel like this is a big confusing issue, because the answer will turn out to be so easy, but only if you look at it right. Our expected discounted payoff framework really is derived and with respect to the agent's information set, what's in people's heads. And the E and the beta that we're referring to is their subjective expectations about the future. But fortunately, we can derive implications that we can test from this. So an important feature of an asset pricing model is it should not refer to quantities that are just in people's heads, because that's completely unmeasurable. We need measurable quantities, and we can do that. Here's how we do that. Our theory says 0 equals E of M times excess return given agent's information, but we can take expected value of both sides of this equation using some coarser information set. If we just take expected value of both sides of the equation, then 0 equals E of MR, the unconditional average. Why? There's this, the theorem is called the law of iterated expectations. The expected value of a conditional expectation is just the expected value. What you think today that you're going to think tomorrow about the weather the day after tomorrow is just what you think today about the weather the day after tomorrow. It's a fairly straightforward proposition, but it has this important implication for us. So we are allowed to take unconditional implications. So when we take the agent's 0 equals E of MR and take unconditional expectations, we derive a valid implication of an asset pricing model derived based on agents' information sets. That's a lovely property. What we do is in fact valid. It's an advantage of the expected discounted payoff framework. If we started with expected returns are conditional betas times conditional factor risk premiums, where all of these conditions are in agents' heads based on agents' information sets, well, we can try again to condition down, take E of both sides, but we're out of luck. Yes, the left side conditions down, but E of beta t times lambda t, Well, you're not allowed to bring the E inside a product. And the beta is a regression coefficient, not just a variable. So it's not true that the average of a conditional regression coefficient is the unconditional regression coefficient. Doing it this way leads you to complicated models of conditional betas and MS. This way, you just swiftly condition down and you can derive correct implications of your asset pricing model based on coarser information sets. So next step in thinking about conditioning information, instruments and managed portfolios. What we did so far is we took 0 equals ET of MR, conditional information on the agent, and we conditioned down to the unconditional mean. You might worry, we're going to lose a lot of power in just looking at unconditional means. Can we do something about that? Yes, we can. And here's the trick. If the agent sees ZT, then ET of MR times ZT, we can bring the ZT in and out. It's a constant from the information's point of view. It's in time t information. And then we can condition down to 0 equals E of MR times Z. That's created a new implication for us, something that adds power that lets us see if the conditional mean is really doing what it's supposed to, as opposed to just the unconditional mean. For example, we could have, based on our first logic, just checked, is the unconditional mean of M times R equals 0? Maybe yes, maybe no. But now we need more implications to generate more powerful tests. Well, if we want to see if E of MR times Z is 0, one way of thinking to do that, let's run MR on Z. And can Z predict MR? That's a more powerful implication than just, is MR 0 on average? Can Z predict it or not? That's another more powerful way of doing it. Another way of looking at exactly the same regression, if you read ahead a little bit, you can do the GMM approach. Simply asks us to look at unconditional moments, E of MR times Z. And MR times Z, that's the covariance term on top of a beta, so it's essentially the same test, but it's another implication. It's from that point of view, we're adding instrumental variables to add power and to let us see whether the conditional, a little more information about whether the conditional mean of MR is 0 as well as the unconditional mean. There's a third way of looking at the same thing. E of MR times Z, we can think of Z as just an instrument or a regressor, forecasting returns in the 70s tradition or GMM in the 80s tradition. But we can also unite RE times Z. Now, RE times Z is a return itself. It's a managed portfolio return. What does a hedge fund do other than look at some signal Z and invest more or less in an excess return strategy according to that signal Z, and then report the return to its investors? So an instrumental variable is the same thing as a managed portfolio return. And now you see that by adding instrumental variables, managed portfolios, that's just like adding more returns to the space. So this managed portfolio theorem is another beautiful uniter of the things we do. It tells us that the time series is the same as the cross-section. Running time series tests, can we forecast with regressions, is exactly the same thing as forming managed portfolios and then doing unconditional tests with the expanded managed portfolio returns. The managed portfolio theorem. An example you've already seen, Fama and French's 25 portfolios. Fama and French, in their table 1, didn't look at individual stock returns. Every year they reformed 25 portfolios using book-to-market ratios and size, which are variables known to forecast returns. So they were exactly incorporating time series information by doing an unconditional cross-sectional test using managed portfolios. Another example, empirical asset pricing uses the returns of hedge funds and mutual funds all the time. What are we doing then? Well, we can just use unconditional asset pricing, cross-sectional asset pricing, using hedge fund and mutual fund returns to see if the managed portfolios they're using to incorporate information tell us something about our asset pricing models. So time series is the same as cross-section. Regressions are the same as portfolios. There's another camp that we don't have to divide. We're really all doing the same thing. Last word here is sufficiency. So you've seen that by adding instruments, we're able to get more and more power. How far can this go? Well, here's a theorem, another theorem. If 0 equals E of MR times Z for all Z in an information set, then in fact we can say the conditional mean of 0 E of MR is 0. In other words, the definition of conditional mean is the same thing as all linear and nonlinear regressions put together. So at least conditioning information set generated by a set of variables, in principle, once you've put in all the variables as instruments, you've got conditional expectation. That's a large set of variables, but at least you know that you're fishing in the right sea.
In the paper, I saw Jensen's alpha, and sometimes researchers argue that Jensen's alpha should be 0. That argument can be interpreted from the third point on the board.
It's actually from any of the points on the board. So I've been writing on the board the version of the asset pricing model that we should see 0 equals E of MRE, right? Then what we've seen before is how to translate that relationship into expected return equals, let me add an I for REI, equals beta I on some factor times a lambda. Jensen's alpha is the definition of the residual from that relationship. So is expected return different from beta times lambda? So when researchers say there's a Jensen's alpha, what they really mean, it's very close to E of MR minus 0. It's almost alpha I is the residual of this relationship. It's the residual of that relationship. It's expected return versus beta. It's this distance here. It's a name for how any of these things is going wrong in the units of expected return.
Thank you.
So the world is not AI. Conditioning information changes over time, and traders see more information than we see. Our last issue on how we can deal with these kinds of problems: conditional versus unconditional models. A problem is that the parameters of a model may vary over time. That's what I call a conditional model. A classic example is the conditional capital asset pricing model. We may say that expected returns depend on conditional betas times a conditional factor risk premium. Or, translated into discount factor language, there may be a discount factor, which is a linear function of the market return, but that linear function may change over time. There are the parameters that vary over time of the discount factor. So we need AT and BT to make the conditional expectation of MR equal to 0. Or, translating again, there is a return on the market portfolio, which is on the conditional mean variance frontier. It satisfies, it is the minimum conditional variance portfolio for every given conditional mean. That's an example of a conditional model because its parameters vary over time. A counterexample is the consumption-based model, which is an example of what I call an unconditional asset pricing model. This is an asset pricing model where M equals beta times consumption growth to the minus gamma. And notice, beta and gamma don't vary over time, at least in this version of the model. They are not parameters that vary over time. That M satisfies the conditional mean of that M times excess returns is 0, and therefore we can condition this down transparently to an unconditional representation, and we can include the managed portfolios and the instruments. This is a well-behaved model. That model is, in some sense, less well-behaved. Now, what's wrong with a model that's not so well-behaved like this, a model with time-varying parameters? Well, here's the problem. Take this conditional asset pricing model and try to condition it down. 0 equals ET times discounted payoff, where the discount factor has these time-varying coefficients into it. Try conditioning down. Can't do it. You can't get from there to here. You can't find a new A and B that are constants such that that implies that. The proof is simply try it and get stuck. You will. So what have we seen? We've seen that a conditional model does not imply an unconditional model. Model is completely conditional with time-varying parameters doesn't imply that there's a corresponding version of an unconditional model. The language is a little confusing because you're used to thinking conditional expectation implies unconditional expectation, but this is different. It's a conditional model which does not imply an unconditional model. Now, a little bit of a mind-blowing implication, since it's very clear how a conditional model doesn't imply an unconditional model. That means that the statement a return is on the conditional mean variance efficient frontier does not imply that the same return is on the unconditional mean variance efficient frontier. Because, well, you've seen the theorems. Those things tie together. So conditional mean variance efficiency does not imply unconditional mean variance efficiency. It's quite possible for a return to always be conditionally mean variance efficient and not to be unconditionally mean variance efficient. Conversely, however, let's look at the second one, the unconditional model. Suppose we have an unconditional model a model with fixed parameters, and that model prices all of our managed portfolios. That's true. Well, of course, if that's true, then that's true. So an unconditional model, which prices all the managed portfolios, implies a conditional model. So the non-time varying parameters, of course, are the same as time varying parameters which happen not to vary over time. That's not that surprising when you see it, but of course the language looks a little bit surprising. The implication for mean variance efficiency is also surprising. It means that if a return is on the unconditional mean variance frontier, including those managed portfolios, then it's on the conditional mean variance frontier. Exactly the opposite of what the language would make you think. Well, mean variance frontier is different from conditional expectation. So this is also a case where unconditional implies conditional, but conditional does not imply unconditional. Now, that's all very fine and well, but what happens when you have a conditional model and you want to think about testing it? I can't just say throw up your hands and go find an unconditional model. And yes, we can come to a partial solution. So if you want to think about the conditional CAPM, what can you do? The best you can do is let us try to model the conditioning information. So if we have, for example, a variable ZT, an instrument that we think is driving our conditioning information, the natural thing to do is let's make A and B functions of the ZT and create an explicit conditional model and see what we can do with that. That's a good idea, and here it is. Let us model the conditioning information, A of Z and B of Z, since we've decided this variable Z captures the conditioning information. And as long as we're making functions, we might as well make linear functions, because nonlinear, Z squared is just another instrument, so all functions are basically linear functions. So modeling the dependence of the parameters leads you to write our discount factor in this form. A naught plus A1Z, B naught plus B1Z, RT plus 1. But wait a minute, now we've got an unconditional model again. We just have an unconditional model with a few extra factors. Instead of M being a linear function of only the market return, now M is a linear function of also the variables and the product ZT times RM, or that's another managed portfolio in itself. So a conditional CAPM and one information variable ZT is equivalent to an unconditional three-factor model. And that's an interesting view on where multi-factor models may come from. Multi-factor models may just reflect conditioning information driving around the parameters of an ultimately conditional one-factor model. In any case, it unites together lots of different things. Any conditional factor model can be re-expressed as a larger number of factors in an unconditional model. Of course, it's only a partial solution, because to do this, I need variables ZT that I can see. I can't use variables Z that are just in agents' heads. So if you truly believe there's a conditional model where A and B vary around based on just agent information, I don't know how to derive unconditional implications of a model like that we can test. So what have we learned? Conditioning information matters a lot, and I hope I've sensitized you to information sets. The agent's information set, the variables that we include to forecast things or as instruments in a study, or just unconditional means. Those are three different information sets. Don't confuse them. Good models don't assume that agents only see the variables we see. Good models recognize that agents and markets see way more than we see, and they derive correct implications that condition down to the information set that we can see. Finally, another great unification. Time series is really the same as cross-section. Instruments are the same thing as managed portfolios. Fama and French reforming their portfolios every year and looking at unconditional asset pricing is exactly the same as somebody else who might run regressions and model time-varying conditioning information sets. They're just different ways of expressing the same ideas. Use the one that's simplest and most beautiful for your application.
You mentioned that the time series and cross sections are the same, but in terms of actually testing this, how would you write out the regression equations that you would be testing?
Yeah, let's be a little bit clearer about that. Here was where I stated the theorem, and I called that an instrument in a time series regression or a cross-sectional regression. Now, there's a bunch of different ways you could do it. This might be the clearest, for right now, the clearest example of testing it using the time series. So I have a discount factor model, And this just says I make a time series regression. Can I predict the discounted return? And if my discount factor is correct, I shouldn't be able to predict the discounted return. So you're clear what I mean by a time series thing. And the way we typically do that is we first forecast returns, and then we see whether the model removes that forecastability. So it's really about, can I forecast returns? And it very much a regression context.
Right.
Now let's think about the cross-sectional thing. From this inspiration, what you might do is so RE times Z is a portfolio return. When Z is a big number, if Z is 2, I put $2 in. If Z is 3, I put $3 in, right? So it's an amount of money invested in that portfolio. E of MR, we could demystify it by writing it as E of R ET plus 1 times ZT, that's the portfolio return. Is that equal to, we'll have some beta times lambda, which is, we're corresponding to the factor pricing model. So a pure Fama French style cross-sectional regression would be the cross-sectional way of handling exactly the same question, is does our discount factor correctly include this conditioning information in asset pricing?
Okay.